Hey, welcome to Coffee Compiler Club, talking about anything, everything to do with compilers and runtimes and code gen and backends and front ends and type systems. And we're all being recorded and we'll all show up on YouTube in a few hours or a few days, depending on when I get to it. And that's my starting spiel. And then Levo had been trying to ask questions on Discord. Did you want to start with a question, Levo? Or
Uh,
ask for a demo of simple, which is what you were kind of hinting at.
kind of have a question. It just wasn't intuitive to me that you would need a never node because when I wrote my prototypes, the control flow was implicit, and I was able to like figure out what nodes link to where. So it wasn't really intuitive to me that you need a never node to reach back because
Yeah.
don't you, wouldn't you be able to easily walk the control node to figure out the parents? And like, I
Right.
didn't know why the control node didn't solve the problem.
Okay, so there's a walk forwards and there's a walk backwards. And in an infinite loop, by definition, it doesn't exit, so it never hits the end of the program, never hits stop. So a backwards walk looking upwards toward the start will never enter the infinite loop. At some point, you typically hit an if that conditionally sends you into the infinite loop or not. So if random exit else infinite loop. And then walking upwards from stop, you hit the if random and you keep going up to start, but you never hit the infinite loop unless you reverse directions. So then it's like, what do you do? Why do you care? And what do you do? So going forward, you could hit the infinite loop, but you never get out. So going forward, you start, you hit an if, you hit a random, exit, or into the loop, and the loop's infinite. Well, it turns out there's a bunch of graph algorithms that most optimizing compilers do many times, actually. Honestly, it happens a lot, where they want to do a backwards walk, but they want to visit every node. And you don't visit the infinite loops on a backwards walk because they're not connected to stop. So the never node is just an easy hack to enable straight up graph walks right on the theory as it's written in the textbooks. Like you could always fake your way around it by changing the textbook theory on how the graph walk goes to handle a case where you didn't enter the loop from below and blah, 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 and you screw around, you make it work. Um, just a lot easier to come through and say, one time only, I do this funny walk where I walk it backwards and then I walk it forwards. And when I hit a node going forwards that I never hit going backwards, I found an entry into a region with an infinite loop. It doesn't have to be a simple region. You can have all kind of complicated shit. You get start, you got if random, exit, else. I said infinite before, but now I'm going to say else if. And these two ifs branch off their own two unrelated infinite loops and other complicated control flow that always goes to some infinite loop in the end. So the backwards walk visits this way, never hits those infinite loops over here. The forwards walk hits out, but it hits the infinite loops. As soon as he hits it, and he says, I didn't get you on the backwards walk, and you just put a bit somewhere in the bit vector to say I didn't get there. Now I have a region of code that I've never inspected on my backwards walk. And at that point, I go ahead and throw in a never node just so I have a hook to get me out to the exit. And I don't put it on the if random choosing between random infinite loops or whatever. I actually go find all the loops and break each and every one of them with a never node. And the never node is a never branch. It's a branch with extremely low frequency, is how the optimizer thinks of it. The optimizer assumes it, in fact, will take the exit to the breakout to exit, but with frequency that's so low that you can't really measure it, which means you're connected to stop. Program semantics are the same, the probabilities and the frequencies are the same, but a standards backwards walk as written in the theory textbooks will visit every node.
Okay, so I guess that's a while, or the loop node might not be connected to n because it's infinite.
Yeah.
But so the way I did it was you would just have like a false case that's connected. So I never thought about never node because I always had a false case.
Right. I optimized away the false cases, got into this
Oh,
never situation, and then put them back in. So let me go find, let me
no,
see if
no,
I
it,
can.
it makes a lot of sense now because I just did it differently and just didn't realize how differently I might have done it.
Well, so if I'm writing a one pass compiler that's just spitting out code as fast as I can, then I don't run into these issues. This is only when you're trying to do optimizations. So the obvious first one pass compiler approach is just you hit some code, you spit some code out, and you keep moving forward. Enough breadcrumbs so you can handle if then else's and while loops and shit. But you don't have to worry about this because you're doing only forwards and only in one pass. There's never a backwards pass. If you wanted to optimize and the generic optimization says, I have an if test, which is constant valued. I know what it is. I'm going to remove it and straighten out the control flow. Well, if you have one of those and it's the exit, the only exit out of a loop, and you straighten it out, then you have an infinite loop. So as soon as you have an if test, which is usefully being used to clean up dead tests, you run into infinite loop problems. So that's like a straight up, look at this cat attack on the camera. Straight up thing to do. You got an infinite loop. We have a dead test remover. You want to remove dead tests. Now you got infinite loops. You got to deal with one, you deal the
Yeah,
other. Fine.
makes complete sense. Yeah.
Okay. We talked a bunch on Discord about the peepholes related to neighbors. Um, I can run a live demo. I can do slides, which you've surely seen before.
Maybe live demo.
You do a short live demo. Does anyone else want to ask something before I head into a live demo on Simple? Because several people have seen this and know what's going on with this thing. And Levo's just now getting excited about it.
I probably seen it already, and I just did the I just reread the chapters because it's been a couple of months. So
Sure. Okay, let me get rid of that. Let me find
Well,
Zoom. You're not being helpful here.
if you're going to spend some time talking about simple, I'd be pretty interested to know what you're doing on the array stuff. Just like
Yeah, right.
could
Okay.
say, or maybe like go from the demo that these guys want, then sort of seg into that or something. I don't know.
Yeah, let's go. So I have a mid optimization because somebody on Discord poked and said, "Hey, this doesn't optimize." I'm like, "Oh, that's easy. I'll do it." And it's mid hack. So let me not do that one. What am I doing here? Oh, I'm getting Zoom. Zoom. Did I share? You guys can see the screen, right?
Yeah.
Okay.
Yeah.
Then you make the font way larger on my laptop, so like
Yeah,
it's way
right.
too small.
Yeah. Okay, hang on. View. God, it's hiding from me today. Um, okay, is that big enough? Or do we need to go bigger?
That's better, thanks.
Okay. So like here is a canonical, this is exactly one of the cases I was just optimizing, but I'll just do it here. Here's a canonical case. New int makes an array, set some values, load some value. It's like as simple as you're going to get. But the difference between this and chapter 14 is that the math for all fields are all done with math that's now friendly to arrays. So let's go do this thing. And I'm going to go parse here. So let's go find the parser where I'm going to say something about parse. Parse statement. It's like parse expression or something. There's a new. How about new again? Here we go. Bam, 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 bam. Okay, so let's start with a new. So we run in, we parsed a new. Okay, so a bunch of things going on here. I can look at my parser, and this is the leftover piece of the program that I have not yet parsed. I've parsed the keyword new when I said match new. Now I'm going to pull a type out. Okay, types got fancier. So this is one of the things new in chapter 15 because I have to support array types. So I'm going to grab the first token that comes out. That's tname, that's my int. If you look at the grammar for simple, if you're parsing a type, there's always a type name first. There might be a trailing question mark if you're nullable or not. It might be a primitive type like int or float. It might be square brackets, any number of which, with some question marks interspersed. So we start with some type name, int. We look it up. Oh, we have it in the type table. So that's, T0 came up with something. If it's not there, it could be a forward reference. So I have to deal with that. So now I'm going to ask a question. Do I have a trailing question mark? I do not. Do I have a square brackets? I do. I do not. Why do I not have square brackets here? Hang on. Ooh, that's interesting.
Hmm.
Type 1, Lexer, no forward ref, I'm out. What did I do here? Where is my parser? Oh, because it's a new. Yes, this is correct. Okay, so now what happened here is because it's a new, I have an array length. The bracket to bracket is not yet parsed. I don't know if you can see this, Matt. The display that I get out of IntelliJ for there is not very helpful. I don't
We
know
can
how
see it,
to.
I think.
Yeah.
Okay, so it's basically the square bracket square. Oh, here we go. Is not part of the type now. The type is int, but this is the length of the array. So the type system says it's just an int because the new guy says, oh, and this is because in the doing of defining how arrays are typed, you can have any number of square brackets, and then the last dimension gets the length. And if you make a multi-dimensional nested loop, the inner dimensions get mentioned first, but they're all null when you build the initial array. Here, I don't have a 2D array, so it's just now that I get the match on the square bracket. My parser string sitting over here says it's the length 2 I'm about to parse. So I parse an expression. The length comes as a constant 2. That's great. I then look for the in square bracket. Oh, I'm going to do a type array. Make an array of type whatever. This is me getting the type, but it's also going to do a bunch of things with aliasing stuff. So aliasing changed a little bit, not really. I know that if you're a type of the array body, which is int, if it were a pointer type, it's all nullables. And you must declare your arrays of linked lists or your arrays of persons as nullable arrays because they all start at nullable. Go make a name up for you that's got square brackets on you. I look you up in the array of things that I've already done. I already know about square bracket or type arrays. So I'm going to be done and say, I made you a type mem pointer. So your type is, here's this type descriptor. You're a pointer to an int array. Int arrays are structs in simple with two fields, a length field called pound and a body field called square brackets. You can't type pound and square brackets as a field name normally, so that looks a little weird. But arrays otherwise behave like structs with these two fields. And then I go to a new array where I go grab the array base and the array scale, and that comes from the struct array type. Struct array here has these two fields with the length and the square brackets, and the :2 is the alias for the thing. So the length does not alias with the body. And I can go ask these guys for their base and scale because that's a special for array types. And he just goes and asks the body type here, what's your size of, to know how big the scale is. So coming out of here, I see that I have a base of 8 and a scale of 3. What's the base? Base is the part I'm going to start for the body of the array at. I skip 8 bytes for the length. There's a really stupid limitation. Arrays in simple have 64-bit length. And then I have a scale because ints are 64 bits. So that's my scale factor, shift left by 3. Then I go ahead and do a size math, which is an add of the base as a constant and a shift of the con and the scale and blah, 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 blah. And it optimizes out to be a constant 24, but maybe some math involved to get your size if your size is variable. So now I make a new struct of size 24 because an array is a struct. And this is the same as before, where I just make the thing as a struct and I jam all the fields in and build your aliases and make a new node and put the alias hooks onto the start of the world and everything else happens exactly the same. And I built a node, a new node, whose name says int on it, but he's the same node I would make for a struct. I can't tell the new doesn't know the difference between a struct or an array, other than his length input. He has a couple inputs control where he's built the length, which for struct is fixed by the definition of the struct, but for an array is counts the length. And then two alias classes for the length and the body of the array. And he returns the projection, which is the pointer to the array. So
Why,
out of
why do
there, I
you
get
wrap it? Why do you wrap it in a projection node?
because the output of the new has several outputs.
Hmm.
And one of them is the pointer, and one of them is the updated state of memory, which is the alias classes for 2 and 3. And so I have inside of the new gone to my parser's current scope of the universe, whose input lists have 2 and 3 now. Let's see if I can. And that 2 is a pointer to the new node. So alias 2 is now pointing to the new node because I can have a length field for this new, and it would be a different length for an array of floats, or different alias for array of floats or array of Persons, and so on and so forth. This is a standard alias classing thing, except you have these two alias fields. Also, I now actually store the length in. So the new just pre-zeros memory of size, whatever I gave it, that's the semantics. And then I store, using this magical field name, the length in. And everything else here is fairly standard. Update memory according to the alias for alias number 2 here for the array length. Where's my alias 2? And its bottom type is some integer, and it's storing at alias 2, and its pointer is used as the base of the array, and there's an offset. Let's cover about offsets here. And then the length is the constant I had earlier. And then there's nothing special else going on. Let's go look at some offset math here. So inside the store node, that's not what I want. I want to go inside, there's mem alias. Here's offsets. Okay, what are offsets? So new in the universe here, I have in the types for structs, which are doing things with arrays. So I have a accessor that I can tell struct as an array. If you are an array, I can ask for the array base, and I go compute this offsets thing and grab offsets for field 1 and offsets for, or the scale comes to field 1 and does log size. So also new is log size. What's offsets? Well, offsets just says compute your offsets and then go load it up. So what's offsets here? Well, okay, so it's the offset for each of the fields. And it's this thing I'm highlighting on the left. Field 0, which is the length, is at offset 0. And the base of the array starts at offset 8. And then the maximum length of the array is now at 16. And that's computed when I go do this offsets math. So this is also new in chapter 15. Go compute your field offsets. And I do more or less a radix sort over the field types. So it works fine for structs, and for arrays, it's like way overkill. I only have 4 log sizes, your byte, your 2, your 4, your 8 bytes. Those are my sizes. So that's the 4 counts. And I go ask everyone for your log size, and I count each of the different fields at the different log sizes, and we'll run that math in a minute. Then I basically write them out in reverse order using packing with padding between things of the wrong size. And then I roll up the sum math and write it back out into the field. So you can ask for a field and get its offset. And then the field's length is the max of the array, and it's just rounded out to alignment, 8 bytes alignment. So I can look at any structure and tell you what its field offset is. And therefore, since array length is a field in an array, in a struct, it's a field in a struct, I can go give me the offset per field of pound, the length field. Well, it turns out to be offset 0. And then I'll do the store there. So return a 0 and comes out and he does this. And I've made a new array, and I'm unwinding from the parts of the new array. And I'm going to unwind a few layers before I come around to the end of this expression. And this expression was something like type name equals expr. And let me update. I'll be done with this expression in a minute. I have a variable. It's well defined. It's not an integer to be widened. It's not an integer to be narrowed. It's not a forward reference. It needs to be filled in. I validate that you're not insane. And now I'm going to update the type. So XS will be assigned the value of a projection of an int array. I'll do that assignment, I'll unwind, and I'll go into the next statement. I won't go to the next statement yet. So basically, if I go to my chapter 15 test, I just did this, and now XS is defined as an array of length 2.
So one thing is that you don't have a node that specifically, like maybe in a syntax, abstract syntax knows the array that represents an array.
Yeah,
we represent them with the instruments that we already have,
yeah.
and we implement maybe the size of the array is implemented as a add node and something by the schema, and you peep hole it so it will fall to a constant, maybe.
Yeah. Yeah, here it's a constant. It doesn't have to, but yeah. Yes, so moral philosophy, especially when doing compilers, reuse where the semantics allow it and look hard for those kind of reuses that make sense, that don't cause more confusion. So it's a little bit stretch to have a type struct be a type array, but it's not a big one. In the past, I've done type arrays as a separate thing, but they only have these two fields, the length and the body. And they're very, very close to a struct. So,
but the benefit, we represent arrays as a struct, we can do the same kind of a math with a struct also, maybe.
Yeah. So the structs do the same thing. Well, let's go look at a struct, right? There's some really junky structs here. Let's see if I have a struct with any more off fields in. I know I made a bunch of big structs later in life to test out the thing. I'm looking for structs that have like more than one field in them. And here is some evil fuzzer generated case that runs on forever. Does he say struct in there anywhere? Whoa, look at this very common cut and pasty name for structs. All right. How about you? Oh, wait, I saw one. Yeah, here's a bunch.
Yeah.
No, next an I. Oh, that's fine. And here's a forward reference, a little more obnoxious. Here's a nice looking one. Okay, so let's go do this guy.
It's a linked list.
Yeah, it's a linked list. So he says a struct LLI linked list is a linked list that has an optional nullable next and an int. Okay, and the head of the linked list is null. And then I say, while arg is true, make a linked list entry, put the next to the head, set the arg in for I. Head is now this new entry, and I subtract one from arg and go again. I just count down arg and I make a linked list of length with the numbers squared through it. Then if my head was empty, give it up. Otherwise, grab head off next. And if that was null, return a 1. Otherwise, I get the value. And all I'm trying to do here is validate that I can chase the linked list 1 or 2 spots and pull a value out of it. So that's the whole thing. There is if I pass you an arg of 0, the list is of length 0 and head is null, and it returns a 0. If I pass arg with a 1, your next value will be a null here, and I'll just return you the 1. And if I put arg of 2 or 3, then or 10 or whatever, he'll do next of I of head.next of I, which will give you a 2. And that's what the evaluator claims, and blah, blah, blah. So here we go back to type struct and offsets. And I didn't run this guy, so there was stupid here. Where did it go? Chapter 13, here, this. Run this guy, dude. So I'm about to make a new struct, somewhere in the middle of a new struct. Okay, so let's go get some context. Parse statement, parse some assignment of some otherwise thing, roll down, parse primary of a new. Okay, so let's go look at the code that I'm going here. We get a little more context, which is chapter 13. So this struct got parsed as a definition, but I didn't do the offset math because no one's used it yet. Somewhere in the universe, I'm going to say, that's the first time I make this struct and I do something with that struct, right? So that's the first time I know anything about, or I need to know something about the struct. Like at this point, I need to know the size. So over here, if I'm looking at, I'm making a struct, I didn't match on the square brackets. I do have a TMP. It's a type mem pointer to, a linked list structure. So I go ahead and pull that out. Now the object is the structure. If it has null fields, it's a forward reference. I disallow you saying new of a forward reference type. I ask, are you an array? There is a missing array length thing here, which I don't think this code is ever executable now. This is probably test should go away. So here I am, make a new struct. How big an object do I want to make it? Well, constant of whatever this is. Well, that's the offset of the length of the last field, which will be actually the length of the whole struct with padding. So now I'm asking for, give me the size of the thing. Okay. Looks like I hit continue one too many times. Here.
When
And
you're,
now I'm in the offset.
getting the offset, that was a call to con, so you're actually generating a node there, right?
Yes. This con will generate me a constant node because it'll take a constant integer. So con takes a primitive constant.
Yeah.
And
I just want to make sure that we're not talking about an actual, just a number. We're talking about a constant in the program.
Yeah, that's because structs are fixed size. Arrays have to have the variable length, but structs do not.
Yeah, okay.
So wherever I do new array here, he comes in, he says array base, array scale, size is a node. It's not a constant. It's whatever you peephole when you say shift left the length by the constant scale and add, do an add of the constant base.
It's a math that has to be done at compile time.
Has to be done at runtime.
At runtime.
At runtime. Yeah. So let's say array of length arg, where arg's what I pass in.
Yeah,
In
but
fact,
if it's a constant, then it will it compile it?
And if it's not a constant, he's going to take arg, shift left, and add.
You have to do at runtime. You don't know. Okay. Cool.
Yeah. All right. So then I'm back over here at offsets, and all I'm trying to do here is say, how big is this struct? He has two fields. There's a cache for the offset computation. It hasn't happened. I have one field of alias2 that points to pointers to himself, and one field full of ints. So the math here is really stupidly easy because ints are the same size as pointers, I think. Actually, maybe not. Okay, fields. Go to the first field and get his log size. Yes, why did you not single step? How about now? Okay, so here I am asking a type mem pointer for his log size. And I say I'm using 4-byte pointers and 8-byte ints and 4-byte pointers. So in fact, there is something interesting happening here. So log of your size is 2. I throw in there. I go to ints and I ask, oh, you could be int 8 or uint 8 or bool or 16 or I32 or U32, any of the above, right? And so you have to be a declared integer type, which is only the ones that you get by you naming it. In theory, you can't get here. So in theory, if you picked a type, you can compute ranges. The system will handle arbitrary ranges for integers, including negative and positive and misbalanced. They don't have to have anything weird. They'd be all weird ranges. But a declared type uses declared type names, which are always these nice powers of 2. So the declared type of the array comes here. This case, it's int, so I'm going to roll down here to this bottom. It's the bottom int, and this the max size. But if you make an array of bytes, you get a smaller size for the field. So an array of bytes. You make a struct which has byte fields, they will be small fields. Then I say, okay, now I have a count, and the count here is it's one guy of size 2 log 2 and one guy of size log 3. And then I'm going to go do the math from the biggest guys first down, and I'll pack the big guys first, which just means that you have an offset, which is the current value of 0, and I throw you in for the first field, and then I grab your size, and I so on, and walk through all 4 sizes. And now I have offsets here, and he says the log 3 guys, the 8-byte size guys, all start at offset 0, and then they stack up. And the size 4 bytes start at offset 8, and then they stack up. And the size 2 byte and the size 1 byte all start at offset 12, and then they stack up. So then I come through here and I go grab each field in order, because your fields might be numbered out of order. And here they actually are. The first thing mentioned is this 4-byte pointer. The second thing mentioned is an 8-byte integer. And I'm going to swap the offsets when I do the layout. So I'm grabbing the first field. Its log size is 2. It's the pointer. I go grab from where the pointers will start. They'll start at offset 8, and I throw you into the offs array. So field 1, the pointer starts at offset 8. And then I go to the next field, the same alignment, and I count down my field count so I could assert, which I never actually did. The count's junk. Turns out the countdown meant I now have no more fields of offset of size 8, of size 4, log 2, size 4. The next field, however, is a log 3 field. He comes from where the log 3s start at, which is at 0, and then I go bump him and run his counts, and I'm actually done. And so the offsets now are field number 0, the pointer is at offset 8. Field number 1, the int, is at offset 0, and the size I compute right now is the rounded up max size. And I require you to go to 16 because I had a 4 byte, an 8 byte, and then a 4 byte, and then I'll round you up to 8 bytes. So you get size 16, and then I return 16 for the struct. He goes in, makes a constant out of it, and then I fill in the constant fields, and that's just, the start of the thing, and it's done. So that is doing this guy with struct offsets. But now let's go. Oh, the other big change here is doing loads and stores. Yeah, okay. So this is dot identifier because I'm doing a load or store on a struct or square bracket arrays. The current guy I'm doing has a bunch of field loads and no arrays. So let's go ahead and see what happens here. Okay, so the parser says I'm about to parse dot next out of dot next equals head, gets assigned a head. And go look at my code here. Where's the full size code here? This I'm about to do here. Okay, so I already parsed X. I'm going to parse the name here. The name is the next field. The type of the thing is, well, I'm expecting some kind of pointer type. I have some unknown things, there's some dead code things, there's some for ref things, those are all sanity checks. Okay, so go ahead and look up the word next in the type of the thing. And he came back and says, oh, you're a pointer to a linked list entry. So this is recursive self pointer to a linked list entry. At the base of the type, that's a linked list entry guy. Go find where you are in the base. So the base has a next field. It's field number 0. More sanity checks. Go ahead and pull the field up. Here, field alias class 2, pointer to question mark, linked list. It's not an array, so it must be. So here's the array math for doing a field reference on array. I expect an expression here that would be the array length, the array index, and then you do the math, which is get the base of the array, take shift scale, blah, blah, blah. However, for your struct, you're going to get your field offset straight from the struct. So I'm going to go base offset. What does that mean? Well, I'm in the offset guy. I just did these offsets. And the index is 0 because I'm looking for the next field, which is the 0th field. And his offset is at offset 8. So come back out, make a constant 8. That's my off. Okay, so what is off is offset. Now new structs need an offset. In chapter 14 before, stores and loads took a field name and they secretly computed the offset for the field name under the hood, which meant at runtime, somebody took a name and made it into an offset, which was Zmilia's evaluator doing a hash table lookup, right? I mean, it was JavaScript fields. You did a hash table for every field reference in the actual implementation of the evaluator. Okay, now I'm doing a number and you don't get these hash tables at runtime. And it's a store. There's a double equal thing. So now I have an expression. I'm going to store it. I go compute the expression, which, what is the expression doing here? It is me trying to figure out, oh, look at that. Let's go find the whole thing. Where's the guy? It should be head. Oh, he's going to say there's no thing here in postfix. Name is no, it's none of the above. Okay, never mind. All right, fine. I was trying to single step. Let me come out of the recursion. It's a recursive descent, so you recurse pretty deeply here. Okay. Yeah, there was a look to see in the grammar if you could have another field reference, but there wasn't. It was just head alone. So the value field to come back is some phi of the moment. If I go look at the whole test, we can see that head is in the loop. I don't know if head gets set in the loop. In fact, it does. So there's a phi for the loop head. So when I ask what is head, parser tells me it's some phi function. It's some phi node. And then I do auto truncation or widening or narrowing, and then I just do the store. And the store takes offset directly. So expr is the base, that's the offset, the value to be stored. And then of course the alias class of the store array, and then you're done. So that was doing a field store where I looked up the offset of the field. It's probably most of the new things in this chapter was the math for arrays and the math for fields. So there'll be another lookup here for x.I, which will get me an offset of 0. And then the rest is just math, and then you do math and away you go.
So why do you have the store node have the base node plus and the offset as inputs? Why not just have an add node that adds the base and the offset?
Right. And in fact, C2 does just the add node and then it unwinds to get the base. So in a garbage collected language, you always need the base. And if you look at an x86, he will have, in fact, most risks, well, all risks as well, will have a reg plus offset and a reg plus reg mode. And so one of the regs holds your base.
Because
and then your offset.
Because objects move and has to be always the math is from the base, from something that can change.
It has to be from the base, from something, and the base might move on you if garbage collection. So at that point, the compiler wants to have the base mentioned in the garbage collection info somehow as a separable thing.
Mm-hmm.
And if you have a base plus offset, you have an add.
I see. That makes
and
sense.
You mention it to the garbage collector, he doesn't know where the base is because he has an add, the result of an add.
Mm-hmm.
This happens sort of easily in loops where you do strike reduction kind of things. And you say, well, I have a pointer and I'm continuously incrementing it. And so I have a base, starting a base, and then every time I do something, I do pointer plus plus, pointer plus plus, pointer plus plus. Okay, 200,000 of those later in some long running loop, I stop for garbage collection. What's the base? So you have to track it and tell the GC, this is a base, and this is a derived pointer off of this base. And then the GC at that point can say, oh, subtract the 2, put the offset aside, move the base, re-add the 2, the derived pointer's fixed, away we go. And that's in fact what Hotspot does with C2's derived pointers. Here in simple, I just, I'm not setting up for a giant long-running high-performance GC situation. So instead, I just said, always have the base. So every load and store directly references a base, and there's an offset. And that means if your array math happens, you'll be doing a plus math situation, not a star pointer plus plus. On an x86, that's all like, he just does that naturally anyhow. That's a, fat array math op, whatever, addressing op. On a RISC chip, there's possibilities you'll have an extra add op that you could get rid of, except that everyone's wide issue and can eat add ops for breakfast. So the runtime costs of doing that are negligible.
I see. Okay. That makes perfect sense.
Okay. So yes, stores have the base directly jammed in. What else here? Parse both fix. Oh, this piece of demo is probably done enough. Oh, I was going to see if I hit the load hack. I was just doing a load hack. Yeah, here's a load hack. It's probably not exciting unless it fires. This is somebody pointing out that a trivial optimization didn't happen. This trivial optimization didn't happen. Okay, what's the value of XS of 0? At a glance, it's going to be 1.
1? Yeah.
Yeah, okay. Prior to this morning, Simple will just give up and say, I don't know. And that's because he was only looking for a load. This is an array load where exactly he saw the array store just immediately prior. This one's in between. This store is in between, and he would just give up and say, I don't know. So can I prove that this store, the highlighted blue one, is unrelated to the load at the return? And the answer is yes, I can prove they're unrelated because I can show that their offsets are guaranteed different. Therefore, they are unrelated. Therefore, I can bypass the store in blue there and look again, and then I can get a hit and go. And that's what I was doing this morning.
Why do you have to deal with something prior beyond the zero address? Can you just see that the array is referencing something that you already know?
Well, suppose I have this code. Okay, now is excess sub 0 going to return me a 1 or a 2?
1?
What if arg is 0?
Hmm.
In fact,
Oh.
I even checked for that right here. Evaluator test with arg is 0.
Oh.
It won't be a 1. It'll be a 2.
Fine. Point taken.
Okay. So the point is that in order to bypass, I have to prove arg is always unequal to 0, which I can't do because it's not. And so I can't bypass.
So it won't constant fold it to the
Yeah,
one.
it won't constant fold this. This won't constant fold.
Yeah.
This will as of this morning. Neither would constant fold as of yesterday.
Yeah. The R1 is you cannot do anything because you don't know.
Right, and there I don't know. So if I instead I go over here to chapter 13 test, these two stores, those are both stores. Those two stores are guaranteed unrelated because I know the next field and the I field will never be the same. Which means that this head.next could bypass a store of the I field. If there was a prior store in the graph, like this program doesn't have it, but you can imagine, I said head.I equals 99. Okay, then I load head.next. Does he care about the 99 stored to I? No, he does not. He goes right past it. And he looks
how did you do so the x in the upper scope, the x.I equals arc are constantly changing, but how you deduce that? So at the end of the scope, arc changes its value. So you can prove that x.next is guaranteed different.
What I can prove is that any field called next is always never related to a field called I. And every type, every struct, everywhere, all the time. If you have a field called next, it is never a field called I.
Okay.
So always I can bypass. And that's directly represented in the graph. We should probably make a graph out of that guy by having different memory edges. Whereas in this other case, the body of XS has the same memory edge. So this one I don't get free aliasing information out of. And this one I do. So let's take this guy. Let's go look at a graph. He's big enough. It's going to be a little bit obnoxious. Let's go look at the graph. After I get rid of all my breakpoints. Here I am attempting okay, this is the new optimization is enabled and didn't crash on me, and it will crash at some point. So if it crashes, I'll just turn that thing off. Here's the graph viz dump. Let me find screen share. And let me go hit share on graph viz dump. Okay, so this is this whole giant linked list thing. What the hell's going on here? Well, yes, it's just hit the point where it's so big it's hardly worth looking at. There's at the start of the world, there's a 2, and I can't highlight things. There's this $2 and $3 under start. That's the memory aliasing edges, where $2 is probably the next field and $3 is probably the I. Memory edges are in blue. And then here I have the linked list. The new in the middle is the linked list. Can I highlight? Can't highlight any of it. Oh, that's because I'm
I
on
think
this. Hang on. Oh, ooh, cool. Try again here. How about sweeping? No, that drags. I thought I had a double click that let me highlight things. Darn it. Okay, fine. This is SVG output. So what else? Someone's going to ask a question. I was going to point out things, but for Levo's sake, the star void, you see the star void underneath the if? That's the null pointer check. That syntax is for a cast. I'm casting you to an unknown pointer that is not null. Cast does a join in the lattice on his input. What is his input? Well, input 0 is control. He's dependent upon the true test, which is testing that the test's head and the cast's head both have a little tiny 1. You can't hardly see the little tiny 1. I can't do anything with it. Points to this phi of head. So what happens here is the if says if head is null, and the answer is on the true side, it's not null. I know it's not. Then I'm going to cast it not null. The value of the void is the join of not nullness and whatever phi of head is. So that's where a join comes in the lattice. It's the better of the two. It is the upwards value in the lattice. It is, I lifted you because an if test at runtime told me some fact. And now whatever head is, I know it's also not null. I know both things. I know whatever it is from being a phi, and I know it's not null. And the phi means he just gets his value from wherever things that feed into him. And of course, he's all confused because the horrible graph layout. But he's like dependent upon the null initially and an arg that got computed, not an arg, a new that got computed down in here, the new node, and gets passed around and assigned and shit. So bad graph for this kind of a demo.
So the purpose of this graph was you're going to show us that the dot next field and dot I
Oh yeah,
field
dot
never
next and dot
alias.
I. So here I
Yeah.
have a dot next assigned. So middle of the field, middle of the graph, I have a dot next equals and a dot I equals. There's two assignments. The memory edge is in blue. It has a little tiny 1 next to them. The 1 in the dot I, almost in the center of the whole graph, points to the $3 off of the new, and the next points at the $2. So those two memory edges are unrelated. Now things point at them, and those things follow the blue edges that come into dot I and dot next. Again, I said this is a bad graph for this, but because they're unrelated, they'll know the dot I load down here at the bottom. I say dot I right before the return at the very bottom has a blue edge. I can follow it up. It snakes around. It snakes around. It comes over here some phi function. It never crosses anything that says dot next. I've broken them apart already. And so I can bypass .i loads around .next loads just naturally in the graph without ever doing any work. And there's no code involved for that anymore. So peepholes that do things like .i coming from a .i assignment never have to deal with a .next because I know they don't exist.
They can optimize separately.
Yeah, whereas array bodies have a natural, everyone's aliased, unless I can prove the indexes can't alias. And there I don't get a free one out of the graph. Let's go grab that. I'm going to go do the chapter 15 stupid easy array guy for the same exact test. And I should have, oops. And I'll paste it back into the guy. And we'll get a easier graph to look at. Okay, so this was the case of make a new, assign 1 and 2, and then load. Okay, so I've made an array. That's the new in the middle, new array int. He has a size 24 in the upper right. I stored at offset 8, some 1. I stored at some offset 16, a 2. I stored at the array length field, which is unaliased from the body, at offset 0, a value of, where's the value? A 2. So it's a 2-entry array. He has 2 other stores on the body. That's the square brackets assignments. The blue edges for the length point around to 2, but they never intersect with the blue edges for $3 to this store and this store. Then I have a return, and the return takes all the memory so I don't throw away the entire array body. I could have return say the function's done, the program is done. So if it's a return from a function, the array's alive maybe if I escape the value or something. If I return from the entire program, I don't need those arrays anymore. The program's dead. I just need the return value. The return value is a 1. So I did the optimization because I was just working on the hack. If I turn that off, the return value will instead be a load. So let's go turn it off and run again. So let me go back to my load node hack on mid hack and let me say, you're just disabled. I have you fairly easy to disable. And I'll rerun. And I'll get another graph. And I know you guys can't see me screwing around with Windows to rerun. So here's a new graph. Doink. Okay. The return at the bottom, oops, has a dot square bracket. That's a load as opposed to an assignment of an array. And he loads from the array body, the blue arrow, to the array body, which is a store at 16 of a 2. He stores at offset 16, the value 2, of an array of a store of a 1, 8, blah, blah, blah. So all this says is, there's the 2 stores where I initialize the array. Here's the load from the array. The load from the array is at the same array base, and I mean the same state of memory, and these 2 edges are merged together. One is an offset 8, and one is the pointer that comes out of the new array. So the bypass logic I added was this load at the bottom can see he's got a store. He can see that the pointer on the store, the little 2 edge, and the pointer on here is the little 2 edge are same. I'm loading from the same array I'm storing. The offset is a constant and it's some number. And the offset for this guy is a constant and it's a different number. To 8 versus 16. That's good enough. Immediate memory from a store. The array bodies are the same. The offsets are different. That the 2, actually, so just the offsets are different. Never the twain shall meet. This load can bypass. Then the bypass logic says, oh, look again after the memory of this store. So follow his memory edge up to this store and ask again. Same question. Can I bypass or am I equal? So the questions are exactly equal, load takes from the store. Exactly not equal, bypass, carry on. I can't tell, give it up, and don't do anything. So,
and I guess a can't tell would be if you got to a fee, for instance.
Yeah, I give up on fees as well. There are some things you can do. So this is exactly alias analysis of any kind or dependence analysis, and you can get infinitely clever and all kinds of giant algorithms and bugs and optimizing compilers. Like for many years, I dealt with optimizing compilers which had bugs in the alias information that were just subtle as fucking hell. And one of the gems or gold out of Sea of Nodes is that the alias analysis is trivial and covers like 95% of what you want it to cover for trivial. After that, you got all kind of horrible things. You can scrape up a little bit more performance out. You definitely find more alias opportunities, but turning them into performance is trouble. So I went with a 95% solution, walked away and said, done.
Yeah, I have built some intuition. Yeah, go ahead, Derek.
Oh, I just want to say, like, the strategy with the fee, I guess, would be to push the load up through the fee. Is that?
Yeah, instead I have the push a load up through a fee and see if that makes progress.
Right.
And then
you check, and then if not, do you undo it, or?
Yeah, I check before I do it.
You do it. Yeah.
Right. The issue with pushing a load up through a fee is that you always have this whole must make forward progress or your work list runs you forever. Yeah. And the obvious one is you have a simple loop and you push a fee up through the loop, which puts 1 on the pre and 1 down at the bottom, which you then discover you can push again and you go again. And you're basically unrolling the loop infinitely. You never stop unrolling the loop.
Yeah.
So instead I guarantee progress before I do the job. And then that's just the simple test on that particular case. You can get fancier things for which you make fancier progress checks. But you fail a progress check, at some point you'll find a program that you hang on because the optimizer never gets out of the damn default loop.
And I noticed in this graph that the new array node does take the 2 and 3, the $2 and $3 memory edges. Is it the same case? They all do. All the news do.
Yeah.
Okay, yeah, it was a bit hard to tell on the other graph.
Yeah, yeah, yeah. Oh, gosh, a mess. So you can go round and around here. What you want to do? The issue you have is future loads must take the merged state of the new that you just did plus prior news. And there must be a place where you merge those states, or else you'll have these funny cases where loads want to bypass forever and they end up bypassing their own new because they don't have a way to find their new by following memory edges. You have to be able to, if this load at the bottom of the screen, I can't point with my finger, with my mouse. If this load at the bottom of the screen happens to be coming from some other new, not the one on the screen, but an earlier one, I must be that I can walk the blue memory edges and hit the other new eventually.
Mhm.
And if I don't, well, then I might bypass my other new. Like I get a dependency problem. So now I have an issue where I have to merge the memory states from all the other news that happened before and the new memory state I got from this brand new my mouse is sitting on now. Where do I merge those states? Well, I can make a separate merge node, and I've done that before. I've gone back and forth in this a bunch of times. There's no terribly better or worse answer. This is an easy one. The new just takes it in. I have had a merge node, a merge mem node that took prior and took the output of the new. I've done, like I said, I've done this a bunch of different ways, but you need to have some kind of memory merge here. This version is a little more conservative and forces you to be smarter when you want to say, I don't alias and I can bypass, in exchange for being simpler. So I lose some opportunities or and move some opportunities into a more complicated flavor of, oh, somebody's saying chat, more complicated flavor.
Manas has a question, yeah.
Manas has a question in chat. Runtime checks for improving alias info. Oh yeah, sure. Yeah, so Manas's question is basically runtime checks to improve alias info. C2 totally does this. This is where I have two arrays. I'm doing like a Daxby, Saxby, something stupid. I have so two long running loops. I'm going to have slightly different semantics of the arrays are the same or different. And then if you have the same thing for having like I have overlaps and I need to know, can I run the loop backwards or forwards and get some different behavior out or whatever, or they're unrelated and then I can just go hog wild. So you put a runtime check in that says, hey, they're different or they're the same. And then what do you do? Well, you got two different versions of the loops. And then how do you handle that? So in the land of C2, that's profiling data. You go ask that question. So C2 only does that if he thinks he has big progress to be made if he proves no alias. So he goes check the profile data. Can I prove no alias? Well, the interpreter doesn't gather that information very often. And I don't know that I ever made the interpreter gather that information. So C2 will start by saying, I'm assuming you guys are not aliased, and I'll put the heroic bit in and go. And then I'll run out code. And then if you deopt, I'll flip the heroic bit and give it up. And I'll make two copies. With profile data, I just make the correct first copy.
How would the graph look like with the second entry of the array was an arg, as we discussed, that it cannot tell.
Oh yeah, right. Okay. So here is me with no optimization, and if you look at the loads, you're asking under this second load here, the first store. I move the mouse to the first store is at a fixed offset 16 instead of a math computed from arg. Okay, so I'm going to go back in. I'm going to unwind. I'm going to put my optimization on. If it triggers breakage, then I'll have to go fix it because it's not done. And I'm going to go to chapter 15 and go change that to setting of arg1. And then I'm going to come back over here and rerun and get a new graph. Didn't crash. Have a graph. Okay. So now I'm moving my mouse to where I have in the middle of the screen the store that all depends on arg. And if you look at the edge labeled 3, the little tiny 3, instead of being 16, it's now an add of 8 and a shift left by 3 of arg. Okay, now with this little optimization that says I can prove aliasing or not, or no aliasing, the load says I have a store in my memory input. Can I bypass? It's not equivalent because I'm at a direct 8 and his math says add. So those aren't equivalent. I say, okay, so you're not the same. Can I bypass you? And I'm an 8 and you're an add, and I don't know. I can't bypass. So he quits and he leaves the load in there.
So why only goes only one step? What if the optimizations prove that the arg goes to a constant in
Well,
a larger program?
if arg has been proven to be a constant, then the add of a shift of 3 of arg will have folded up.
But of course, this cannot be catch at the first time in the program. It has to optimize until it
Right. So
reaches some
peepholes
point.
come along and fix that.
Yes.
So let's go write this program. I'm going to
Quick question while we're looking at this one.
yeah.
If that add had a range that put it outside of
Yes.
the threat, like would that then fold up, or is that just an extra optimization you can do, I guess?
This is how much work I want to do. I get 2 integer ranges for the offsets. Do they overlap?
Right.
And if they don't overlap, I can bypass. I don't have that in there. I have a stupid test that says you're constant, I'm a constant. They're not the same constant because I already checked that you're the same value. If you're the same constant, you would have been global value number to be the same. Since they're 2 unrelated constants, you're unrelated. I can bypass. So I have a very stupid easy check, but it's weak. It only says constant, constant.
Yeah.
Okay. So I'm going to go back to, well, I'll run this guy here with what you said, and then I'll show you the code. Let's see here. I'm going to throw into chat the new program code and then get you the graph for that.
Let me copy paste it to the docs. Yes.
Okay, so wow, it really cleans up. What the hell happened here? So what I see here is that I stored 1 into x of 0. I set arg to 0. I stored 2 into now 0. And then I return the contents of the 0 entry. So this guy says the returns black output edge labeled tiny 1 is the 2. He says, you're returning a 2. I have an array. I'm going to return you the arrays as properly initialized. He's got the array length is a length 2, and the body has only got at offset 8 a 2. And that's offset 8 is the first entry in the array because offset 0 is the length. So x of s of 0 is at offset 8 is a 2. And the store of a 1 in got optimized away. So now I can give you the same graph in between. I almost went this week, I did AA. I could have done this week on an animation of simple doing the peoples. And he will have the store of a 1 and set of arg of 0. But when he hits the store at xx of arg equals 2, he will clean out the prior store of a 1 and just keep folding up things. And then the whole graph collapses. So I can stop it before he's got the store and look at the graph if you care, and you'll see he's got the full thing. But when that second store hits, it kills the first store. It's a store after store. You don't need the first store. And then
you need only the latest.
You only need the latest. That's correct.
I've kind of get it, but alias analysis is definitely more involved. At least to me, it looks simple, but
okay. Let me the test for store after store. Let's go look at the test for store after store here. The whole point of the alias analysis here is it's trivial. I don't have to do anything about it, and it comes out for free here. I say for free. It's not technically free, but boy, is it easy. Share of IntelliJ. Yeah, here we go. Screen share, store, blah, blah, blah. Where's my idealized? Store after store. Simple store after store on same address. Okay. Let's go run this thing here. So first of all, what am I running? I'm running this code here. I say xs is 1, arg is 0, xs of 0 is a 2. That's your store after store. So while running, I'm in the middle of the iterate. So I've completed, I didn't find this while the parser ran. I'm finding this when I finish out the work list after the parser's done. So at some point I did emit the store, and now at this point, oh, at this point I can build you the graph. Let's see here. Graph dot, oh, I can't remember the name. Let's see here. I think it's generate output. Oh, wait, parser has a show graph, right? Why do you not have a show graph? I had a straight up. Aren't you a constant? Oh, I need a parser object.
Hmm.
Oh, I don't have a parser object. I better have a parser object. I probably got one. I have one here. I don't have a parser object. Okay, I have to do this the hard way. Or not do the graph. Let's do the graph if I can get it here. I want, oh, stop dot show graph. I have a stop node. Where? I thought I had a shot. Stop has a. I'm looking for show graph. Hang on. Oh, iterate.
worry.
Type check. Peephole. Iterate. Yes. Where is show graph on iterate? Thought I had it in there. Okay, I have a shortcut that I've forgotten now, so it's not very short, obviously. GCM show. Well, here we go. That's one way to go. Okay, so this and this is the stop node.
Hmm.
Let's see if this works. Da-da-da-da. Boom. Okay. Come back around. I don't need no good answer here for this and that. Here we go. Back to graph pictures. Okay, so here I am in the middle of, I've completed the parse. I'm in the middle of cleaning out the peepholes. I have the return at the bottom has the store of a 2 of the base of the array of the prior memory store of an offset of 8. The prior store is of the base, base of the new. Okay, fine, but it's the same pointer. The values of 1 and the offset's 8. So the lower store is at offset 8. The upper store is at offset 8. Both of them are to the body of the array. I have store after store, same same pointer and same offset. All right, that's what shows in the graph. Let's go back to the code. Go back to my store. Okay, so of the store I'm currently at, his memory input is also a store. So back over here, where is the this pointer? Why are you not showing me the this pointer? Oh, I'm on the wrong level. Here we go. This pointer is a store of a 2 into the array. The prior store is a store of a 1 into the array. So that's the 2 store. So I got ST here. They have the same pointer. So same object. They have the same offset. That works for structs as well as arrays. It's the same field, the same offset. And then there's some safety check here that you had a thing that was crashing. So it wasn't a type mem pointer. It was a bottom or a top or something. And then what is this check no use beyond? Well, this is the aliasing thing that says the first store, that's store of a 1, no one can see other than the store of a 2. It's directly store after store. So I could have had a case I had an if where I say store 1, if some condition, then store 2, else do something else where I load the 1. And in fact, we have those test cases to prove on aliasing.
So the x dot the first store would never be runtime represented. It will be crushed on the
Right
spot.
here, I'm going to crush it, and that's this peephole set def 1 of stmem. So what does this guy do? So the set def of 1. So that's on the this. This is the store of a 2. I'm looking at the object. He's got inputs. His memory input is the first guy. I'm going to get st.mem. Oh, that's the first guy. It's this one here. Debugger object at 1250, same as it down here, st at 1250, and getting his memory input. What's his memory input? Well, that's It's this right here, projection off of a new.
Hmm.
Okay, it's some memory input. I don't care what it is. All I know now is I'm getting his memory input and I'm setting it over my memory input. So my memory would be pointing to this store st. Now it points to that store's memory input. Skips one.
Yeah.
Okay, that makes this store go dead because check no use beyond was saying there were no other users. So let's go look at ST here for a second. This is the one about to get removed. His output size is 1. It is just this pointer. So as soon as I stomp it, it has no more uses and it goes dead. So I'm going to go get his memory edge. I'm going to set def. Set def says, oh, pull you out of the hash table. That's the unlock. Go get the old value for the def. That's the store of a 1. That's the ST. So this is generic setting an edge in the graph. If it's not null, it's not. I'm making the new def, that's the projection off of the new, use the this pointer, the store of a 2. I go ahead and set the value in, which wipes out the edge. And then I have to go remove the corresponding reverse edge. This is doing graph maintenance. And the delete use says there were no more uses. Kill the old guy. So now I go into kill of store of a 1. Put your
Easy.
defs on the work list, assert some things, find your inputs, go yank them all, start doing delete use. What do I kill? I kill the constant 1 as well. Recursively now, kill the constant 1. Okay, come back around, back to the store here. Deleted use of the constant offset 8. It's not dead. 8's in use. Delete the constant to the base array. It's in use. Go ahead and delete the pointer to the new node. It's still in use by the other guy. I just killed the guy, and no more deaths there, and I'm done. And I'm done with the sign. I'm done now with the peephole that said idealize, and I'm done. I'm coming out. Go back to the work list, and away you go. So what I did there now is I said I nuked that edge, and I nuked that store, and as a store of a 1. So at this point, I can go once again, get another graph dump, mid things. Except let's see if I can come out of here. Oh yeah, so we're going to throw neighbors on the work list here. This does no work, but put a bunch of neighbors on the work list. And nothing got killed. I'm back around I'm about to fire the next step on the work list. So let's go look at my graph. Stop share, start share of Dream Puff. Put the new graph in, boom. So mid work list, right after I did that store-to-store update, he deleted the prior store, and I'm at a legal valid program having removed the extra store. In fact, this is the final program state. So that was it. The key hack here is that the aliasing check is almost free. It's pointer is equal, memory is equal, offsets equal, done. Those are all 3 tests, each taking roughly a clock cycle.
Cool. Fun stuff.
Okay. Yeah. Yep. Okay. Well, there you go. That was Levo had said he was going to go do things with, and he didn't understand why. And then these are all kinds of things that he was asking about, and then he's going to go look at it online.
So when you go through it step by step, it seems logical. It seems obvious. But if I stop the middle of the program without knowing what exactly to look for, then
the sum is greater than the parts.
yes.
So the mindset to keep here is what is the invariance? And then as long as the invariance hold, you can just pile on more and more and more.
The important thing too is to how to spot the graph and how to spot the things and recognize what they're doing. So in order to see,
that just
is it
for
obvious?
me, the small graph is what I put in my head to say, hey, this is just program semantics. I store at an address. I store again at that same address. I don't need the first store. Fine. Store after store optimization. I store at an address. I load from that same address. I can load whatever I was storing and replace the load with the stored value. That's the, store after load or load after store optimization. These are all very straightforward things when you look at it at such a small scale.
Yeah, if the piecemeal optimizations, but is an easy way to look at, because it will get too complicated too quickly.
Yeah. So the big graphs are hard to read. There's no denying it. I don't use big graphs for debugging. I use small text printouts, and occasionally I do large printouts, but I always filter aggressively, in my head for what I'm looking for to the small scale, because these peepholes are all locally correct and they're all small. So if something breaks, it's because I have a broken small scale peephole problem. And now, which peephole and where did it break? What did it take to break it? Okay, fine. That one, in fact, there was that load cloning one had a bug was caught yesterday or the day before, and I fixed it also this morning. And that was when I take a load of a fee, and I see that if I poke up through the fee in the two different directions I can poke, in one of the directions it folds. So I'm saying, this is a progress. Let's go ahead and fold it up. There was a case where it wouldn't push up correctly, and it would make a broken graph that was then showing up later as some other thing. And then now, how do you find broken graph? Well, the test case reduces, and you can stop the peepholes at any point in binary search, and you narrow it down to it broke here. And then you can stare at the local graph and say, oh, I didn't handle this case. And then you throw in the cutout. Life is fine. That's the normal, I have a broken graph thing.
Yeah, because these things happen on a small scale, the decisions they have to make are small decisions and they are locally correct, but they can snowball if something is not taken into account
If you have a broken peephole that makes a broken graph, the compiler can prove false is equal to true and fold up the entire program into some stupid answer.
Yes.
Generally an infinite loop or return false or something crazy.
Something happens.
That happens. That's the binary search thing. If you dump the graph in the middle of the peepholes and it already starts to look insane, you can say, I don't know where, but this is not correct. So you pick something that's obviously broken, and then you cut in half your binary search and you look, is this thing still broken here? Like I said, it's generally not too hard to narrow down broken peeps. There are other problems I have in these graphs that are harder to come around when I'm doing fancier shit, which is what goes on in AA. But if I'm doing peephole things here,
what is one fancy thing that maybe becomes tricky to look at?
Yeah, I'm doing stuff with Hindley-Milner inferencing while I'm doing peephole optimizations, and
I imagine so. Yeah.
And the Hindley-Milner side wants some things, and the peephole graphs aren't a tight fit, aren't a perfect fit, so they don't line up right. And then I make mistakes and shit breaks. Okay, fine, but that's not just doing peeps. Just doing the peeps, it's pretty straightforward. But yeah, the sum is greater than the sum of the parts. Total is greater than the sum of the parts. That's what I'm trying to say.
Yeah. So when they're on a narrow scale, it's easier. What are we looking for each optimization? That's.
So like you're looking at performance of. So everyone says, hey, C is the fastest thing. Well, Java got pretty fast. Okay, what was going on there? Well, I made Java code optimized like C code. Okay, why is C code considered fast? Because people routinely don't get faster unless they go to assembly or they start paying a lot of attention or say to mechanical sympathy and restructuring their programs and whatever. C compiler takes care of all the obvious shit that happens in the language translation layer down to the machine code. So does C2 for the exact same kind of things.
Isn't it easier because the C is maybe it's forcing you to think and in the terms of the machine, which is closer on the more closer level Isn't that easier?
Yeah. Okay. So I only put in IR nodes that match machine semantics at the basic level. That's the loads and stores.
Mm-hmm.
Something to do with new nodes and how they allocate memory. Add, subtract, multiply, divide are all basic primitives. You can certainly have CF nodes where you had operators that were doing like matrix multiply. There's no reason to keep it at such a low level. But when I'm doing this, when I'm targeting a low level output, I will start with a low level input. And then I'm forced you to an abstract machine model, which is true across a broad spectrum of machines where you have memory and you have registers. You have pointers and you have, von Neumann architecture.
But typically in a compiler there is a step that's called lowering that it exactly intends to rewrite the high level semantics into low level semantics that are, but we don't see that here. We see here optimizations that happens on a case by case basis, and it's different. So
let's look at the lowering job that has to be done here. You look at simple code, it's like C minus minus or Java minus minus, right? Already it's an abstract machine that effectively maps straight to the hardware. Same as C code does. Pretty much same as Java code does. Java has a few things that require some higher level semantics. There's not a lot. So there are lowering things going on here. So I do null checks baked into, I emit the null checks and I check for them and I'll catch you if you would, otherwise, if I can't prove not null and you have an easy way to prove not null by throwing in extra ifs or whatever. But I do null check elimination, null check proving on you. That's basically a kind of a lowering step. Other things, the lowering is very modest. So that would be structure layout, array offset math, right? And now I get you down to some idealized machine code. That's the idealized IR. Simple does have a path to straighten that out to a control flow graph. CMS. And the next thing that I would claim is lowering is I would go to machine code. It's at a point where I could add register allocation and then instruction selection, register allocation, and be done. And write the bits out and in a buffer and say you can run this code or you can write it to disk or whatever you want to do with it. So there is another lowering step to be done here. But in particular, I am not taking you from some semantics that say I have matrices and I'm emitting out a dense matrix multiply deeply nested loop. But if someone were to write a version of simple that started at the level of doing matrix math and did matrix math optimizations for a while, but then at some point they wanted to say, well, I can't do any more matrix optimizations, then they would have a lowering step to say, here is a giant loop nest. And then, let the optimizer go tell on that. I guess streaming math, the streaming language, the same thing. I have streams and I'm concatenating streams together and do whatever streaming optimizations, SQL query optimizations. Then you lower it down to some IR, which would be something very similar to what I have now. And
the thing that occurred to me that when you say, for example, in these examples, new something or any something, or new struct or new array, they already represented by some notions of a load and store, and they have some abstract. They are boiled down immediately to their most primitive they can be, suitable for representing on a machine so this translation happens immediately. So
the parser says the semantics of a struct that you write is a lot of memory. You said struct s field next question mark field int I field person name field blah blah blah. That maps immediately to I have a memory layout.
So it's immediately geared towards that. It's not
the only interesting extension here would be to add some understanding of basic data structures to the IR. Like think of a hash table that is either implemented as open addressing or separate chaining. If you distract this to individual loads and stores, then that's a very, very low level operation. And you probably have challenges improving aliasing or no aliasing for the
Standard,
cells
yeah.
of the array. So, I mean, you have to basically start to reason about hash collisions in your alias analysis
Exactly.
if you want to disprove aliasing for something like open addressed hash table. But
Yeah.
Swift, for example, does have the intermediate representation level for representing things like dictionaries. So if you write to the dictionary at the same key twice, you can actually treat this as similar to store after store optimization,
Yeah.
which would
Isn't
be
that
non-trivial to do otherwise.
isn't that like MLIR's ideas that these operations go on more?
MLIR idea would be more to enable this because MLIR is not quite itself an IR, it's rather a compiler framework that allows you to write
Ah,
your own IR.
oh, I
And
see.
you can write something like Swift. Of course, there is already a bunch of upstream dialects. So those IRs you write with MLIR, they are called dialects. There is a bunch of them, but I don't think, at least upstream, I'm not aware of any data structures dialect for the MLIR.
So go back to the hash table for a second. The Simple's current design is you can implement a hash table, but I won't know anything about it other than, as you pointed out, what I can deduce from aliasing on a hash table. Same as C, same as Java, right? This is tutorial, semantically equivalent. Suppose I want to extend Simple with the notion of a hash table that I know it is a hash table in the compiler IR, and I have dictionary gets and puts. Then yeah, exactly the same optimizations apply. You can do all kind of things, and at some point you have to lower that hash table down to machine code still. Somebody has to lower that. So, this is like pick your level. I claim CF nodes would work fine on that hash table version, just great, but that's not the target goal. Although if I were to make a language where that was the goal, then I would definitely put a hash table notion straight in it and optimize at that level. Certainly JavaScript treats fields as hashes into structs. They have some kind of a baked-in hash table. I am just certain they have all kinds of hash table related optimizations about the hash table they know about.
Oh, by the way, speaking of lowering, Cliff, I was curious, how early do you do SSA construction? And I'm thinking of the Java bytecode example. So remember, I was asking about this conversion between the stack machine and register machine, because I assume that you have something that is closer to a register machine, right? You have like SSA virtual registers, but you
Um,
start with something that is still a stack machine, which is JVM bytecode. So how exactly do you go between these two? Or
okay, fine. So you've seen the talk on simple SSA, right? I've done.
yeah.
Okay. So in the realm of JVM bytecodes, the stack slots are perfectly not aliased. They're never any dynamic computation of stack slots. They are just a compressed version of the registers. And I unroll that compression the obvious way. The
So
parser
stack slot
maintains it.
number equals register number or translates to register number, basically one to one is what you're
Yeah,
saying.
there's a one-to-one translation, except they're not really to the registers. The registers are independent from the stack. So I have a pile of stack. The stack grows and shrinks. At any point when it grows, that's a new effective register number. And when it shrinks, that one's just gone out of scope. But the next time it grows, it's a new unrelated register than the one before.
So it sounds suspiciously straightforward, but why are there
It
like
is.
papers about this and
I
everything?
don't know. I knew how to do this shit literally in high school. I did a fucking fourth optimizer thing, very, very primitive. But the stacks were obviously known, completely statically.
I wonder if there are some tweaks or caveats that they ran into. They did mention in one of those papers that when they did apply this straightforward number scheme, they did end up with vacuous moves, like move from one register to another and then from
Oh,
another to one,
but
which is a simple peephole, but right?
right. The fucking folds away as you do it. Like you
So
never
I'm not
even see
missing
it.
anything. It really does seem to be straightforward. Can
Yeah, I
you
don't
think of?
understand myself. So
I
one of the
wonder
things that
what it is.
maybe is the difference is that I'm p-polling while parsing. So this crap, like I get a move. I never even never make a move instruction.
Mhm. Do
Never.
you do you already do some SSA constructions like finotes insertions? Like if you are say parsing something that corresponds to two branches of an if, are you gonna be inserting a finode on upon reconvergence, or you don't
Yeah.
do that at this
No,
phase?
no, no. They're made at the converge point. You have a scope. It has a list of maps from names, which would be register numbers in the bytecodes and the stack offsets in the bytecodes, or names in simple, as a map to the IR that came before. Then you have an if. And the if says I make two copies. I make two copies of the same mapping, the true and the false. I run them again. Then I have a convergence point. Then I do a merge right then and there. If you haven't changed, I don't need a fee. If you have changed, I put a fee in. It's just that simple.
So you do that also at the same stage you are parsing, say, JVM bytecode.
Yeah, I'm building SSA as I parse. That's what
On
simple
the
SSA is
fly.
all about. It's building SSA as you parse. We just go do that in the debugger right now. This is not a hard thing to do. Let me find a suitable. That's a little big. Let me see if I can find an if test that's a little smaller. Then I'll do it. Well, here's a stupid one that this is pretty obvious as well. Sure, let's do this guy. So die. Oh, that didn't help any. How about
Even
you?
something like the G, that could be either X or A, depending on if you end
Yeah,
up with
it's
one.
X or A. Right. Okay, so test passes. Okay, let's stop here. You get to here. Okay, what is it? Where does this come from? Well, we're in the parser. Let's do parse if. Okay, here we have parse if. Set a breakpoint. Run. Okay, what am I looking here? So the yet unparsed is some expression to be null checked, and then an if and an else, and the rest of the program. So that's where I'm at in the parser. So I'm going to parse the predicate here, which came back and said it's a knot of r divided by 13. So I have a predicate. I put an if node in. I put a true and a false projection in. So here's, if true and if false. And these are literally just nodes that say true and a false. I've also cleaned up the test a little bit, so the if went dead. But I have another if on these projections that just inverted. I got rid of the not. So if true became some if of arg of divided by 13, I got rid of the not by flipping the test. So there was a peephole right there. Now I'm going to run along and hit this code. It says parse the true side. Okay, somewhere in here I said, oh, I missed. Here you go, dupe. So I have two scopes. I have a true scope and a false scope. They were the dupe of each other. And false scope is kept in a register in a local variable. And true scope is kept by the parser's underscope internal state. I'm going to parse just that side. And I just did it. And I now take that over into tscope and I shove false scope back into the parser state and I'll parse the false side. And then we'll look for an else there is. So we parse. We're doing a little pred unkeep here. We're going to do some stupid checks. We're going to go shove things in. And I put tscope in, but here it is, merge scopes. Okay, let's go look at merge scopes. Okay, what's merge scopes do? So I have a this scope and a that scope. The self pointers are scope. I have a that scope. This scope, that scope. We'll look at the breakout. This scope says dollar control false. Arg is arg, A is arg over 3, B is arg times 5, X is arg times 7, Y is P, Q, blah, blah, blah. There you go. Here's the other guy. Hey, control is true, not false. Arg is arg, A is arg over 3, B, C, X, Y, blah, blah, blah. There's a bunch of things here. I get some names. That's like a stupid thing. I don't need it. Here I have a thing. Here it is. This is the big one. If this is that, I don't need a fee. If they're different, I do. So let's break here. Let's break here.
The semantics of this comparison, how deep are you looking at the equality to conclude that this is the same as that?
Exactly the one pointer. There's no depth.
Okay.
Literally, the two values are the same value or not. So the n of I is the ith input of the scope, this scope, and this is the ith input of the that scope.
And you basically compare the incoming nodes. Do you do some kind of hash consing?
So I do, but it's not important. It's unrelated. I could get rid of this test and put a fee in every time. But then I would immediately peephole, and the fees peephole would say, my left-hand side is my right-hand side. I merged the same two things. I can disappear. And so this is a performance hack. This cutout is just a performance hack. It says, don't make a fee that you're going to immediately peephole away.
Mm-hmm.
But I don't need this test. I could make the peep. I could make
No,
the,
no, just curious how far it is optimized. Like you would pick up something just because of you are also running the peak calls. You would pick up something like 2 + 2 on one hand and
yeah.
4 on the other end, right? Because at this point we can count on peep holes having been run.
Okay, let's look at who we did and who we didn't verify. I is now 6. I ran through the this and the that, and I said, at the top level of this, 0 is the region. I was started at loop at 1. R didn't change. A didn't change. B didn't change. X didn't change. Y probably didn't change. It's 0, 1, 2, 3, 4, 5, 6. Looks like G and H, I'm about to do number 6 here. P. P was the first time I got to change. Let me go look at the program that I just
Can you
did.
show me, can you expand this and that just so I look how your ints are represented?
So this is this. This is that.
Do
He
you
has
have,
inputs.
aha, those are inputs.
And now I have,
Ah, so you essentially have some access to the scope of this and
this is the
what,
scope. This is literally the access. You have to have access. You must. It's a parser. And this is that access.
and you compare the environment, so to speak. So what are the
Uh-huh.
values and
Yes.
the variables and their values? Okay, okay.
So slot 1 on both says arg. It's the same arg. Slot 2 didn't change. Slot 3, 4, 5, 5, same. 6, I get a difference. 6 here is arg over 11 plus arg times 7. Here it's arg times 5 plus arg over 3. If I go look at the test, I said, you're at 1, 2, 3, 4, 5, didn't change. Oh, wait, P, how did P not change? Well, X plus Y and A plus B turned out to be the same at some point. Maybe P was the front. Oh, P didn't change here. I have to go look, or maybe my count's off. And then G, which is going to be X or Y, and H.
That should be different, right? Because,
Yeah, P should be different. Let me go,
yeah.
let's go look here. So I got through. There is one, but I don't tell you what the mapping means except by the names that came for free out of the mapping. So, oh, this is ARG. This is A, B, C. This is the names that are just for debugging purposes. So arg A, B, C, X, Y, P is number 6. So that is the first difference. It is P, and P is changing. Yes. So I'm putting in a merge for phi for P. So that's P coming through here, and now I'm looking at number 7. I is 7. It's G is changing, and you get a phi for G, and you're going to get a phi for H. And then I'm done, and I kill the dead scope, and I keep one of the 2 scopes. So I made 2 scopes. I ran to the end. I merge them together, and I throw one away. And I keep the
Okay.
one who carries on.
That seems eminently reasonable then. Okay, interesting.
I'm telling you, Hotspot's been doing this for 25, 30 years, and no one's
I
complained.
I wonder how would this correspond if you have an IR like MLIR with the basic block arguments. I suppose instead of inserting phi at this point, I would have to create 2 blocks and then just feed those 2 different phi values as 2 different arguments to those blocks. But otherwise, that should be equivalent, right?
Um, yeah, I don't know enough about what he's set up, but if you're taking it from a CFG with basic blocks and you have the list of arguments that are live in, then yeah, you have to be uniquely named already. So you have to
Right.
have SSA named live in arguments.
Right.
So I mean, I don't know what his right, I don't know what his invariants are, but yeah. So that I mean that's what you just saw there is like the thing for doing easy SSA. Just walk the names,
And
insert
construct
a
this
piece
on the
different.
fly. Okay. It's interesting because it seems straightforward, but it is pretty different than LLVM does it.
Well, it doesn't give you minimal SSA. And
Right.
after peepholes run, you get closer to minimal, but you may never hit minimal. But in practice, you're so close that like I said, no one's ever cared. So
Right.
I don't have any proof that a minimal directly, but I can show you that I usually get hugely more than what minimal does, hugely better, because people do other things. And so people who run minimal SSA and then do a bunch of people work and then come back and rebuild SSA and then do more people work, they're like doing it the hard way. And in one pass, you get minimal and the peeps get you better than a classic no peeps plus minimal. I'm way faster, way smaller, way better than a classic do it all without any peeps, run SSA, peephole away. I'm just hugely better this way.
Yeah, I wonder how something like that would work for C and C++.
I claim I have gotten, I didn't do this exactly for C, but I did close. So I certainly was well aware of C compilers and were doing this for C-like languages at Rice University. And at that time on the corpus I had as a grad student, it was doing great. Now you had aliasing in C that broke out, I mean, stopped a lot of other optimizations, and you wanted the other kinds of aliasing going on that I wasn't doing at that time. So I couldn't tell you about the next piece of C of nodes for C at the university scale 40 years ago because, I didn't have a good aliasing answer. If the aliasing answer for C comes in, I'm going to, by default, like do what Yasser says and says, you're always perfect aliasing. You're never cheating and lying unless you put the cheat lie thing in. And then I can just generate the aliasing parts separately if you claim I'm breaking your aliasing rules. If you don't claim you're breaking them, I'm going to assume they're not broken. I can just do the same perfect aliasing I'm doing now. But certainly the SSA on the variables, I can just do like I do now.
Right.
And I was doing them in grad school and on C-like language and like simple, some stupid ass thing for grad students to go generate code for. What else here? After the merge scopes, we'll come out and then I'm at the parse statement and I'll stop and give you can I give you a stop here? What do I call it? Maybe. This is in the middle of the thing and so the trailer hasn't happened yet. Oh no, he's not, nothing's alive. So it's, you get nothing. Let's go stop here because I don't have any wired in a stop yet. So I can't do a graph dump until I get out. Darn it. All right, let me come up here. Now let's try again. Wow. Pretty dumb. Boy, he didn't clean that one up. Oh, I wonder if it's one of the earlier ones. Is that really correct? That looks suspicious. This program says return P minus R. Oh, he in fact knows the test claims it should be a 0. Yeah, I should have gotten rid of the test. He should have cleaned it out even more. Why didn't I clean out? I have a region with no merging. I should have cleaned it out. Ooh, there's a missing peep. Fine. But the test turns into, is R divisible by 13? Do nothing, return 0. Hey, look at this code here. Is R divisible by 13? That's the question. The result is P minus R. What's P? P is A plus B, or X plus Y on the left and the right. And then minus R is G plus H. That's X, that's A. What the hell? It turns out if you do the little math, you fold peeps, it's all peepholes, that P and R are equivalent. And so it goes away. Yeah, and you kind of see it here. P is X plus Y. G plus H is X plus Y. P is A plus B. G plus H is A plus B. So I have a X plus Y one of two ways and an X plus Y one of two ways. And then after the merge, I compare the X plus Y and the A plus B versus the other flavor of X plus Y and A minus B. And
So functionally, it is a little bit like you already have value numbering for free.
I have value numbering for real also, not just for free. Yes, I have value numbering. Yes. Global value. Let's see global. In fact, this almost surely hits global value numbering. Let's go look at hit global value numbering. Yes, go find me people ops here. Global value numbering, GVN. Oh, I hit it. Well, constant null, it hardly counts. More nulls. Lots of nulls. Here's the parser happening. Oh, here's something. Oh, another constant null. Of course, here goes. arg13 got hit twice. The if of arg13 happens. That's because someone is p-polling the partial if. Here I am folding the false and the true projections to get rid of the not. So the original code is bang arg over 13. The new node is just arg over 13. So to do that, I went into the p-poles for this control proj. I'm running down here and I say, oh, flipping an if test, remove the not. I call it twice, once for the true side and once for the false side. So that's why I hit in the GVN on the if node. But I can CFG control flow just fine, and I'm doing so right here. Get rid of the parse. Let's see if we get any more hits there. Here's the expected hit. I have a phi merging arg times 7 and arg over 3, and another phi. They are different. They have different node IDs, 37, 39. They're two different guys. One's labeled P, one's labeled G, but they tie up in the global value numbering for merging the same nodes.
Would it be beneficial to record which peepholes are a code is run in a sequence? So some kind of a flag or some, no, not flag, or maybe even name them, and you say on this code first run this peephole and this peephole, then global value numbering, then this peephole. Would it be beneficial at all? Maybe?
Well, this is for helping you understand how it goes. I thought about doing that exactly this week. Would be build a graph every time the parser adds a node, and build a graph every time a peephole does a change, and then use the graph tweening code. I still had in my inbox to do graph tweening code, which should be able to tween between repeated chunks of graph that have small changes.
Like a diff between
Yeah,
optimizations?
graph diff. Yeah, he would take this graph and mutate it to give you this graph via just the diff parts. I have the basic wrapper of it lying around, and then can I make it do 100 diffs here? So here I stopped at global value numbering. I can also stop at places where I made progress for other reasons. And these are all the places where I typically make progress. So found a constant that's new, value numbered. Of course, I hit the repeated self constants. I'll clean that up in a second. Did some sort of idealized rewrite. Everything else is just made normal progress. There is another piece of progress that I'm not showing, which is I find a new type, but the new type doesn't change the graph, but it does say I know something more about some node in the graph that I didn't know before. So I can also stop and look at those if I want. That would be where the type improved, and in fact, the old was not node. There's always one you get in the beginning when you first make a node. So now I'll rerun the program, and let me see that I get rid of stopping for constants. So I'm not going to look at value numbering, especially constant 0. So what do I happen here? So some idealized happened where I started with a node that says a bool of equals 0 should be replaced with a not. So that's a transfer. That's a people right there.
So you are talking about to record a transformation between the graph, but I'm just talking simple entries. So this peephole global value number happens, then that code elimination happens, then in sequence. So would
just
it be
write out this, that?
Yes. Would it be beneficial?
Not to me, but maybe to somebody. You sound like it would be beneficial to you.
Well,
so download simple, go into this middle of this peephole. It's very clearly labeled peephole ops, and all the places where he returns something other than a null, down at the bottom here's a return null. Write a line out and just standard out and lines out and see what you get. And
another
then
thing,
if you can tell,
it comes to mind. We've talked about this, but unclear. If you record the abstract syntax tree, and you keep it around along with your transformations, can you be able to tell?
Right. So the first thing is that you don't have a tree. Very
Yes.
rapidly, you don't have a tree.
Okay. If you pin to something else, maybe line of code, maybe this line from 40 to 50 suffered.
Yeah, I can put some sort of, I want to say rope, some sort of collection of short string snippets that every node the parser builds, he built because he got from some string snippet. And then every time you do a global value numbering, you merge two things together, you would join the snippets. If you replaced it with a constant, you would probably merge snippets. It's very similar to global value numbering up here. I just carry the constant through. They have a constant, just carry the where it came from through. Idealizes more trouble because he does things that are nonlinear, as you can't just say, you have to case by case basis say, what's it mean when I do this? Right? Where do I take the where this came from and move it somewhere else? Maybe I want to say it came from here, but at this point I also did something maybe with this other thing, and now you're building up in an imagination in your head some track of what the optimizer is doing in order to get the final result. And of course, the optimizer is very carefully defined to be, I can run these peoples in any order at any time. So there's complete order and variance, but I will get different results in the middle while I'm busy doing things. The end result, I claim I'm trying very hard to have a church roster property. You get the same answer in the end always. But in the middle, whatever order the random graph, wow, got you.
Yes.
Well, even on this example that we're looking at here, if you look at that hash zero constant, like the string that would be attached to it would be almost the entire program.
Right. Oh yeah, right. There's a lot of zeros come around, and everyone gets initialized to a zero. There's a lot of I made a con zeros. A lot of these zeros, by the way, I could get rid of by I have a shortcut specifically for constant zero that I could be using. But if you were tracking where it came from, yes, you would be. Hey, I got another use of a zero. I got another use of zero. I got another use of a zero. So let's go find all the uses of zero.
I mean, in this case, it's really that it's not even that it's a zero, but it's all that logic in that program where it's eventually folds up to zero. And so basically, if you're tracking all those, like I have this thing where I'm attaching source lines to nodes, but then so far I don't really do anything with them, but I was sort of hopefully will eventually. But as I'm creating them, but then yeah, ultimately you just get lots of source lines attached to nodes. And then, yeah, like there are peeps where like all that folding that happened where you end up with this one constant zero, like if you're pulling things forward.
That's what
Seems to me that the correct string that you'd have on that zero would be all of those like calculations, even the if statement and everything.
I'm going to show you where some
zero there.
So here's a zero. I said int g semicolon. Well, it got initialized to zero. So I made a zero here by taking the random type of whatever the type of the variable is and give me the initial value for that, which is always either zero or null. So I could turn this into a shortcut that said, give me the constant zero I've pre-baked. And then I can skip the whole global value, make a node in global value numbering away. But that's a trivial case. Here's another one. I'm going to go up to where it came from. It came from.
I think you're sharing the wrong screen here.
Oh shit! Which one? Oh, you're right.
We are staring.
Thank you.
At the
Go try again.
Yeah.
Okay. So what I did here. Hello. Why did you not rerun? Because Zoom grabbed you. How about now? So I'm running this evil fuzzer test. And I'm looking for, I found a new zero that's going to value number to an old zero. It came from where the parser came from here, came from parser says int g. Here's the reigning unparsed program. I just parsed int g. It's initialized to a zero. Right here, I said new constant, make me the initial constant. This is always either a null or zero. I got a zero. I run again. I go back up. Where did it come from? It came from int h semicolon. Okay, that's the second zero. Here I another zero. Where does it come from? Something right after the end here. Let's go find what I'm looking at. It's going to be, oh, this is probably actually the int h. I just finished parsing the h. Parse expression name. Oh, name is h. Yes, I just now did h. I did p, g, and h. Those are three zeros. Now I got another zero. Where's this one come from? Somebody say parse me a literal zero comes from some Lexer parsing of a zero. It turns out if I look at the parser, I've just passed the if. I go back to where the test came from. I see a zero right there. That's the next zero. And again, I could shortcut that one out. So I got 3 zeros in a row. Now I have this case where I idealize and I say a bool of equal equals zero. I'm just going to redo a not of the expression. So I replace the bool with a not, and one use of the zero goes dead. Then I have a true projection. I'm going to invert the test and say, oh, you're going to be the false of the opposite test. Back in here, here's an if. Here's a second version of the same if I just made because it went for true. Now I'm doing for false. Oh, here's the false. You're now going to be replaced with the true version. So this is me just negating the test. So it's again Pete. So I've hit the 3 zeros I just made. I got the if twice. I've got the true and the false flipped, and I'm just now moving on past that. Here I have an add of, and I don't tell you what it was before, but almost surely this add flipped the math so it canonicalized results to more optimistically get a good answer out of it. Somewhere in the parser, I'm just computing something right before G here. So let's go see the first guy. I just did this. And I'm just about to parse G equals X. So I canonicalized X and Y so that I could hit them if somebody else did another version of X and Y that were swapped around. I'm canonicalizing this one, arg times 5, arg plus 3. Okay, where does that come from? Come back up to the parser. I'm still at right before G again. It's the second half of G equals A. So if I come to the whole program, it's the second half. I'm down here. I just finished this one, canonicalizing those adds, about to parse G again. So canonicalizing things. Here I have a phi, and the new value is an add of a phi. So here's a phi of an add turned into an add of a phi. This is the part where I can discover these things are the same. So the phi says I'm a phi of a region. That's the merge point. The left-hand side is arg 11, arg plus 7. The right-hand side is arg times 5 plus arg times 3. Ugh. I have a phi of two adds of random crappy things. Well, I'm going to pull the add down and say I have an add of two phis of crappy and crappy being merged. So the add is in the middle. There's the plus. Left-hand side is arg 11 merged, arg times 5, right-hand side, whatever, crappy things. So straight up, I got rid of one add op here. I had two add ops, and I now have one add op and two phis, but phis don't make code. Again, I have something and I'm restructuring it, and it's probably post-reconstruction. He's probably canonicalizing the order. I don't know what he did in the ideal call here. I can't tell. Here, I found two phis that are the same because on the one guy, I plussed through the phi and I made another phi, another phi. Well, eventually I came around and I looked and said, this phi and the one I got from the other guy, they're the same now. So there's that one. Here's another one. Arg 11 came in twice from two different directions. Well, here's another one. It's the giant add of the giant add of the two things are the same now. The two adds are the same. Oh, I found a new constant. Subtract node is saying I'm going to produce some constant value 0. Why? What are my two inputs? My two inputs are the same inputs. You can't see it in the whole print, but the two inputs are the same value. Add at 1563, add at 1563. This is the final subtract where I say P minus R. I already know that they're the same. I'm still parsing the program, but I already know I'm returning a 0 here. So I'm going to replace the subtract with a constant 0. Next one, found a new constant 0. Where did it come from? Came from here. So the new constant 0 is the same as any other constant 0. And I'm done. So I did like 8, 10 peeps, mostly canonicalization. I inverted this test, then I inverted the whole if. Then I took this add and pushed it up through the phi or pulled it down one of the two directions and did a little global value numbering. Suddenly, this became 0. And as soon as it became 0, I didn't show you the kill. As soon as it became 0, I killed everything. The whole rest of the program just dies. So, what did we get here for? Oh, you're asking what to do with ifs? No, wait, how did somebody fold up? Whatever. That's what's going on here. Good. By the time I'm not even doing the iterate, by the time I'm done parsing, I've already folded 90% of this program. This is a junk program, but 90% of it folds away coming out of the parser. And again, this is one of these, the parts or the sum of the whole is greater than the parts. Why is Zoom telling me something here? Oh, because chat's trying to talk to me, right? Because somebody wants to have a thing. Adrian goes, hey, there you go. Okay.
Yeah.
Well, maybe we can be done here.
Yeah. Yes.
Oh, looks very relaxing, you Canadian, you.
Yeah, I moved to a more tropical location.
Yeah, I'm
Actually,
thinking it's better. It's better. Generally the little outline around your head is not so visible as it used to be.
yeah, I think it's actually better when you add this one.
Oh yeah. Oh my
Now,
God. I
now
used
I
one of
feel
those.
like I'm.
Oh, Jesus. Cameron does the one where it's just like zoomed in on his face and it's like re-imaging how his face works and it's uncanny valley. It's really bad. It's like, oh God, don't do that. Whoa. But this one's just, cut and paste your head around a
Yeah.
background. It's a little better. All right. Good talking. I hope Lilo
Yeah.
gets his answers.
All right, I'm gonna like change the channel now.
Yeah.
Yeah.
Bye-bye. Oh, that's good. You didn't get left or right mixed up either. All right. Bye-bye.